Hi, everybody. I'm very glad to be here. Today we are going to talk about APTs way, evading your emulation-based network intrusion detection. My name is Ali Abbasi, and I am PhD student in Distributed and Embedded System Security Group at University of Twente here in Netherlands. And well, I did my master in China on PLC security. And well, before that, I was working as head of vulnerability analysis and penetration testing group in Iran National CERT in Tehran, Iran. And my colleague, Yos.
Yeah, I'm a master student and I'm a master student and a research assistant at the same group, and where I do research into advanced persistent threats and unknown malwares.
Yeah, we just have one microphone. Okay, so let's start. Well, we start first with the history of exploitation and shellcodes, very fast, and then we will give you a very brief introduction to emulation-based network intrusion detection approach and the adaptation of it. And then after that, we will talk about how they detect the shellcodes in the network streams and their heuristics. And after that, we will talk about the evasions we designed, and we will have demo beside that. And after, we'll have question and answer. So, 35 years ago, around 35 years ago, first time you had worms, which was first time using buffer overflow attacks, and they were using shellcodes to exploit the systems. And then time by time, it gets evolved by like using more complicated techniques, using polymorphic shellcodes, like there was new encoders and whatever. So it changed time by time, and it became more and more advanced. So normally, the detection was based on like the very basic one was like signature-based network intrusion detection systems to detect the attacks, and it was like basically based on looking at the return addresses, if you have multiple NOP instructions, the shellcode signature, or even if you were lucky, then you could even detect some polymorphic encoders based on their signatures. Well, it wasn't very, very efficient because the attackers could change some part of their codes, and then you couldn't like detect it. And of course, like government-supported attacker or like more sophisticated attackers, they could make their own custom encoder and decoder for the shellcodes. And well, there was always the problem that you have to always maintain and update your signatures. And that's a big problem. Then you had a new approach, which was emulation-based network intrusion. Well, there was a lot of benefits in the emulation-based network intrusion detection approaches. Well, first of all, it could detect polymorphic shellcodes, regardless of type of encoder you were using. And it was not vulnerability dependent, which means that even if you had a zero-day exploit, it could detect it. And it was basically based on some heuristics and like kind of blacklisting some behaviors of the shellcodes. And so basically how it's working is based on you have a pre-processing step, which you look at the network stream, and then you select a suspicious network stream, you emulate it, you generate the execution patterns, and once you generate the execution pattern, you match it with certain heuristic, which is a behavior of a shellcode. And once you matched it, then you generate an alert and saying, hey, this is like a shellcode in a network stream, which probably means that somebody is exploiting you. Well, and then you had a lot of projects adopting these approaches, right? Yeah, and well, a lot of famous, even Honeynet project. Hi, guys. Yeah, so they adopted such approach, and for our work, we choose two emulation-based network intrusion detection for proof of concept. So first one is NEMU, which is a, let's say, state-of-the-art emulation-based network intrusion detection with a lot of heuristics let's say, most advanced until now we saw. And another one is LibEmu, which is a simple emulation-based network intrusion injection, which basically detecting shellcode, which is very, very simple.
Yeah, I'll first install this. It's too bad it didn't have two of them. Yeah, so basically, what does it look like in, can you hear me? Yeah. So what does it look like in practice? Obviously first, the emulation system will have to find a way to detect whether a given network stream actually includes shellcode. So it does this by having a pre-processing step which looks for the characteristics of so-called getPC code. For those who don't know, most shellcodes will need to have a way to find the program counter in order to refer to their own body for further decryption purposes. So two characteristics of getPC code are usually the so-called, I don't know, yeah, if you can see over there, are usually a call or a FPU store environment instruction, which store the current program counter somewhere in memory. Once these instructions are detected within a network stream, it considers the network stream as a potential candidate and it skips to the emulation step. Yeah. So it skips to the emulation step, which is basically straightforward from the point where it detected the getPC instruction. It starts emulating it using, for example, an emulated x86 instruction set and supplementing it with a generic memory image for supporting, like, for example, API calls, having some local variables which the shellcode could refer to in order to generate an execution trace which is compared against certain heuristics. So there are several heuristics which are used to detect shellcodes. The first and the primary one, which is getPC code detection. So obviously it already detected some getPC seeding instructions, which is why it marked it as potentially suspicious. And if the shellcode subsequently refers to the memory location where that program counter was stored, it considers it as malicious because it executes getPC code. The second heuristic is the so-called payload read threshold heuristic, which means that if you have self-modifying shellcode, you obviously have a lot of read operations over the shellcode body for decryption and subsequent writing of the decoded plaintext. So if the emulator sees a lot of read operations to unique memory addresses, and this number of read operations executes a certain threshold, then it considers it as malicious. The third heuristic is also based on the behavior of decoders, which is the write execute instruction threshold. Similarly, when you're decoding a piece of shellcode body, there are a lot of operations which are being written to the recently decoded memory area, and if you execute shellcode instructions from a piece of memory which has recently been written to, then it considers it as malicious. So NEMU added a lot of additional heuristics to this, which are mainly based on Windows shellcode, but similar heuristics could be developed for Linux. So the primary one, which is kernel32.dll base address resolution, which we'll all discuss in detail in the next slides. The second of which is structured exception handler based getPC code, and the third of which is process memory scanning, also known as egg hunting. So when you have a piece of shellcode which runs on Windows, you're obviously going to have a need for calling certain APIs, for opening network ports, downloading a file, doing whatever you want to do. So in order to do this, you need to know the addresses of the certain APIs, which are located in certain libraries, and you need to load those libraries, and you do that with functions which reside in kernel32.dll. So first of all, you're going to have to need the base address of this library in order to perform any functionality at all. So EBNIDS usually considers base address resolution of this library as an invariant for Windows shellcodes. So one of the ways to do this is using the so-called process environment block, which is located in memory for any process, which contains, as you can see over there, a pointer to a linked list of all the modules that have been loaded during load time, and the second of which is traditionally kernel32, so you can trivially obtain the base address. This is one of the things that NEMU blacklists. Second way to obtain the base address of kernel32 is using so-called backwards structured exception handling walking, which involves basically walking the structured exception handler train all the way to the first structured exception handler frame, which includes the default structured exception handler, which usually lives in kernel32.dll, And then once you have a pointer inside the memory image of kernel32.dll, you can walk all the way backwards until the portable executable header, and you have the base address as well. This behavior is being blacklisted by NEMO as well as base address resolution. So when they developed this, they noticed that there was another way to execute getPC code without having getPC seeding instructions by using the structured exception handler. The thing is that if you construct a custom structured exception handler, and then you trigger an access violation by reading from an invalid memory address, you execute your own custom structured exception handler, which includes a pointer to the structured exception record, which includes a pointer to the violating instruction, which is your program counter. And then you continue execution, having a pointer to your own body for subsequent decryption, as you can see over here. So this behavior was added as well as a heuristic, and executing this behavior gets you blacklisted as well. Finally, there's egg hunting. For those who don't know, egg hunting is usually when you have a piece of shellcode, a small piece of shellcode, and you have a large piece of shellcode that was put in memory earlier using some other method. You search throughout the memory for your egg, and then you execute the egg. In order to do this, you need to iterate through all memory pages, and you need some way of telling whether a memory page is valid or it isn't, because if it isn't valid, you cause an access violation. Your shellcode doesn't execute. So they usually use system calls to check, is this memory page valid? If it is, we check all the bytes for our egg, and we execute our egg. So this behavior is being blacklisted as well. So yeah, this is a very high quality clicker. So we found a couple of evasions, which we categorized in implementational and intrinsic limitations. So the implementational limitations are basically limitations of these particular systems we looked at, which could possibly be mitigated by a lot of additional research effort. And the intrinsic limitations are, in our opinion, limitations which are intrinsic to the concept of EBNIDS. So even like other implementations couldn't address these. In the case of the pre-processing and the heuristic steps, we found implementational limitations, and in the case of the emulation step, which is integral to the entire process, we found limitations of both kinds. So what kind of intrinsic limitations are there? Well, the primary one is the unavailability of context data. If you have a piece of shellcode which is being run against the target machine, then obviously the context of the target machine is different than the one of the network-based emulator, because you're going to have a different usernames, different times, CPU ID, all kinds of information which is present on the target system but cannot possibly be present on the emulator for reasons of scalability. You can't have like memory image of everything that's running on the emulator. So by including information from the target environment in your shellcode, you can prevent emulation by the EBNIDS and thus prevent detection, which we'll discuss methods for in detail. The second limitation is the execution threshold. Obviously, for reasons of guaranteeing a decent throughput, the emulator will need to decide after a certain time of emulation to drop the emulation and say, I didn't detect anything, because it doesn't have all the time in the world for every possible packet. While the attacker can easily wait half an hour or an hour before his payload executes. So exploiting that is another intrinsic limitation as well. And the third limitation is the fact that EBNIDS cannot deal with fragmented shellcode, which is scattered over multiple non-consecutive network packets. So what does unavailable context data look like? Well, obviously the first one is non-self-contained shellcode. Think return-oriented programming. Because obviously if you have a lot of return-oriented programming gadgets which are present in the application on the target system, but the same gadgets aren't present on the emulating system, then you can execute the shellcode and thus not obtain like a memory trace and compare it against heuristics. The second way to exploit unavailable context data is using so-called context keying, which you can see right here, which is a relatively straightforward way by encoding your plaintext body using a key derived from information which is only present on the target system. So say, for example, I know I'm exploiting a target system that has a particular username, then I obtain the username, encrypt it with the username, or the CPU ID, or information like that, and then have the decoder basically be a decoder that obtains the same key and tries to decode the body. If that information isn't present on the emulator, then it can emulate it, and thus it cannot blacklist it, and it says nothing's going on here. So exploiting the execution threshold, that basically involves using a very straightforward solution using time stalling code, which tries to time out the emulator before it can actually detect something. And as you can see here, which is a piece from the NEMU code, it decides after a couple of instructions, it has reached a certain threshold, it just drops it and it says, I detected nothing. We tested this using very basic techniques like opaque loops and intensive loops, which are documented in depth in the paper we published. And using integrated loops, which is basically calculating the decryption key based on the operations executed by the loop itself, so it actually has to execute. And using the random decryption algorithm, which is the following. It's also fairly straightforward. It basically involves encoding your getPC code and your shellcode body using a randomly generated key, then generating a hash of the plain text of the getPC code and the shellcode body, throwing away the keys, and having the decoder basically brute force the key, and upon every key candidate, check whether the plaintext body matches the hash. If so, we can continue execution because we properly decoded it. If not, it basically tries the next candidate. I mean, this takes a long time, like 1 hour or something, which is affordable for an attacker, but again, not for the emulator, which times out. Fragmentation is a very rare condition, and it really depends on the kind of exploit you want to exploit. But there are a lot of exploits where the payload gets scattered across multiple network packets. So for example, if you have an exploit which concatenates certain information from various network packets, then it gets spread out over the network and the shellcode isn't present in one condition while it is being evaluated, and thus not all the information is present and it doesn't know how to handle them. So the results were obtained by, in the case of context keying, using a modified version of the context keying encoder which is present in the Metasploit framework module. This encoder was detected by NEMU, the normal one, because it uses a piece of getPC code which is detected. So we encoded the getPC code as well using a context key, and in that case it wasn't detected by any of them. Exploiting the non-self-contained shellcodes was achieved by dynamically building a getPC code and a shellcode decoder out of ROP gadgets against the target vulnerable service, and which was then run against NEMU and libemu, neither of which detected it. The execution threshold was exploited by implementing all types of time-intensive loops and a random decryption algorithm. libemu wasn't capable of detecting any of them. NEMU was capable of detecting the two most simple ones, but not the intensive and the random decryption algorithms. So Ali is now going to give a demo, and I'm going to give this to him.
Thanks, Jus. Okay. Okay, just put it here. Yeah. It's easier than change it every time. Okay, so before I demo, I have to show you something. So we just made an application which run basically our shellcode. So just running one sample shellcode we have. Just want to show you that the shellcodes are working and they are not some random application. So this is just one of our polymorphic shellcode we designed, and as you can see, it's running correctly. And just to make you sure more, I just open it in Oli debug and open the application as test and set my arguments to run my shellcode. And let's restart it. And I have to set a breakpoint before it starts, which I already did before. So let's start it. So it hit the breakpoint, you can see there. I'm just running it, and okay, the basic idea of this shellcode is that it's looking for previous stack frame. I will explain it to you later, but I just wanted to show you that it's working. So, okay, now, well, I'm going to demo the stuff, but before that, I have to show you how it looked like when our, for example, NEMU and libemu, two test cases for our shellcodes, detect the shellcode. So you have to first know, once it detected, how it looked like. Right? So we just made some bunch of bash script to make the process faster. Okay, so here we are testing a simple polymorphic shellcode against libemu, and okay, so here is the command we are running, and as a result, yeah, Thanks. Yeah, you can see the word success over there, which means that NEMO could, libemu, sorry, could detect the shellcode correctly, and it detected that it's a shellcode. And then we run it against NEMO now, against, again, a normal polymorphic shellcode, which is not designed by us. It's just normal polymorphic shellcodes. As you can see, NEMO even can detect the type of the shellcode. So as a result, it can detect, if you are doing a kind of attack, it can detect that, hey, there is a shellcode over in the network. So that was the first one. But now I'm going to demo for you two implementation for RDA, random decryption algorithm, and context keying payload encoding. Again, we made bash script. To just make the process faster, I will show you the one sample source code of our bash script. So this is the libemu. As you can see there, you can see the word failed, which means libemu couldn't detect our RDA implementation. And NEMO. Well, NEMO is different. When it can't detect anything, it don't show you anything. So you see nothing, absolutely nothing. And the next demo is I'm using the implementation for context keying payload encoding. And well, again, against libemu first. This is the command we are running. And again, you see the word failed, which means libemu failed to detect the shellcode. And against NEMO. And again, you see nothing, which means that NEMO couldn't detect the shellcode. Just for make you sure, I just show you example of our the source code of one of our bash scripts. Basically, you can see, yeah, we are running the commands against NEMO and libemu. So it's just wanted to make you sure about it. Okay. Thanks. Well, the problems are not only in intrinsic limitation, but there are some implementation limitation which can get solved, but with more effort, time, research, money, of course. So we made several type of limitations, categories, and first of all are heuristics. Heuristics have some limitation, which is you have to always know the type of heuristic or the behavior of the shellcodes to make a blacklist out of those malicious behavior, right? So if somebody make a shellcode which do not show such behavior, then you can't detect it. And another problem in the implementation limitation is the runtime difference. Your shellcode, when it gets emulated in a EBNIDS, it have a different runtime compared to a real system. And of course, with more effort and time, you might be able to overcome this problem. And another problem is unsupported instructions, which means that there are some instructions which your EBNIDS might not be able to support. Well, instruction sets are time by time gets updated, and well, if you don't maintain it, then you can't execute those instructions. And if the attacker use that instruction, then as a result, you can't, for example, decode your the target polymorphic shellcode, and then you will fail to detect the shellcode. And another problem is that detection relies heavily on the disassembly of the network stream. So if somebody use some anti-disassembly technique you might heard in the malware world and bring it to shellcodes world, then they might be able to evade the EBNIDS. So first, let's look at the heuristic evasion. So I recommend you to read the paper, because we couldn't bring all the stuff which we have in the paper, so we just highlighted the most important ones. And I'm just mentioning them, and then explain the, again, most important ones. So first of all is the kernel 32 address resolution heuristic evasion, which we designed. And another one is, which I will explain it later, so that's why I don't explain it now. And then evading the payload reach heuristic. That's another evasion which we designed, and using a syscall to execute read operation instead of using directly the payload shellcode. And another one is evading the write execute instructions using the virtual mapping, which I will explain. And another one is evasion based on the process memory scanning using SEH walking and API-based accounting, which again I will explain. Let's first look at kernel 32.dll resolution evasion. It's working. Okay, so kernel 32.dll resolution evasion. We designed two techniques to evade that heuristic. First of all is the SEH walking technique, and another one is a stack frame walking, which I just demoed you in the Windows application. So this is the evasion for kernel 32.dll heuristic using SEH chain. So what we do basically is that we follow the next SEH chain until we reach the last SEH handler, which is containing 0FFFFFF, which that's what we look for. And once we found it, there is a pointer to ntdll.dll, not kernel 32.dll, because there's some changes in operating system all the time. So we exploited that problem. And then once we are in ntdll.dll, what we will do is like, we will look for PE header or MZ bytes. And once you found it, there is a fixed distance between PE header and like API called a specific API which we want to load called LDR load DLL. And once you call the LDR load DLL, you can call any DLL you want. So including kernel 32.dll, which is NIMU's heuristic, for example, for detecting your shellcode. So if you do that, and you can call kernel 32, and as a result, you can call load library A, and as a result, you can call any other API you want, then NIMU can't detect it. So if you directly try to resolve the kernel 32.dll, NIMU detect it. So your shellcode get flagged, but if you use this technique, it's not get detected. Well, another technique is basically stack frame walking technique, which means that you have multiple stack frames and you are looking back to the previous stack frame until you reach the first stack frame. And in the first stack frame, you have a pointer to ntdll.dll. Again, you do the same things. You look for MZ bytes or PE header. And once you found your PE header, what you will do, you will try to load LDR load DLL. And once you found the LDR load DLL, at the end you will load kernel 32.dll, and as a result, you can call load library A again, and you can call any API. And then again, NIMU can't detect it. Well, another technique is using payload read threshold heuristic evasion. Well, so the basic idea is that for evading that heuristic, what you will do is like you are allocating a virtual memory using, in our implementation, NT allocate virtual memory. And then what you will do is like, rather than multiple times read your shellcode and copy it somewhere or like put it somewhere, what you will do is like by one time, by this NT-read virtual memory, just by one time, you just read your entire shellcode and put it in your allocated virtual memory. So, and as a result, then you don't have that multiple reads which flag you in the EBNIDS. Another evasion, as an implementation problem, of course, is stack contracted shellcode, which evade the NIMU's get PC and payload read threshold. So basic idea is that you have some XOR, DWOR pushing into the stack, which is like your shellcode, and at the end, you just jump to, rather than like directly calling your shellcode, which is kind of like get PC code, you jump to beginning of your shellcode, which you pushed to the stack, and as a result, then again, you don't do a direct get PC code, and you don't have you don't flag the payload read threshold because you don't multiple times read it. Well, another evasion is egg hunting evasion against NIMU. And in this example, is that basically rather than using a syscall NT at atom, which Joost explained, you don't use NT at atom anymore, but you use another thing, virtual query. So the main purpose of NT at atom is not for detecting if the memory is a valid memory or not. In egg hunting shellcode, you have to know if the memory area is a valid memory address or not, because if it's not, then you are not going to scan it for your egg code or your marker. But you can use instead virtual query, and by using virtual query, you actually it's doing the same and actually used for that, but it's an API. It's not a syscall. Syscall is, you have very few syscalls in the system, but you have thousands of APIs, so you use APIs rather than syscall. And then again, you bypass the EBNIDS heuristic. Well, we have a demo.
Yeah, so I'm going to demonstrate a couple of the techniques Ali just talked about. Is it showing? Yeah. Yeah, so first I'm going to demonstrate the payload read-threshold evasion by doing like this, which is an implementation based on the stack constructed shellcode, as you can see. Oh, wait a second. And as you can see over here, it's first being tested against libamu. Oh, yeah. Yeah, as you can see, it isn't being detected by libamu, and then we test it against nemu. And you can see nothing, which means it isn't detected either. So then we test the kernel evasion, base address resolution evasion technique using stack frame walking, which is first being tested against libamu. And as you can see, a lot of stuff is going on, but in the end it isn't being detected. So when we test it against nemu, you can see nothing, which obviously means it isn't being detected either. Wait a second. Yeah. So finally, we're going to demonstrate the egg hunting shellcode, which is using an API instead of syscalls, which isn't being detected either by libamu, and obviously neither by nemu. So, yeah. So there are a couple of other ways to bypass being detected by EBNIDS. One of which is detecting the fact that we're being emulated. As a couple of you will know, most emulators have telltale signs of the fact that you're being emulated by an emulator, which code can use to detect the fact that it's being emulated. Well, and nemu and libamu are no different. There are a couple of implementational details which mean that, for example, in the case of nemu, all the general purpose registers, as you can see over there, they're initiated to the same constant value. So by using a checksum over all the general purpose registers combined with the constant value and incorporating the result in our getPC code, we can ensure that when it's being run on a normal machine, we run normally, but while we're being emulated by nemu, the code crashes and thus isn't being emulated and thus isn't being detected. So we can do the same thing in the case of libamu, with the difference that the general purpose registers are initiated to 0. Another trait of nemu is the fact that it does properly decode the CPU ID instruction, but it doesn't properly implement it, because it should affect a couple of registers, which it doesn't affect. And by incorporating the effect of a CPU instruction on those registers in our getPC code, again, we can evade emulation and thus evade detection. A more general purpose way to detect emulation at all is using timing, because obviously emulating an instruction is always a fraction slower than actually executing it, especially if you're not using like hardware virtualization, such as the case in EBNIDS. We do this by using timing. So we're executing a loop of no operation instructions, and after that we're executing a loop of computationally intensive operations, such as FPU instructions. And then we take the ratio of those two instruction loops, and we compare it against the threshold, which is the normal threshold for normal machines. Because obviously it's going to be orders of magnitude higher on emulation systems. And then we incorporate this result again in our code to prevent proper execution and thus detection. So Ali is now going to demonstrate this.
It's hard. Okay, so it's so here is the emulator detection. So once it detects it's being emulated, then it's not decrypting itself. So first against libemu, as you can see, nothing. No, of course, you see the word failed, which means that libemu couldn't detect the shellcode. And then we use it against NEMU, and you see nothing, which means that it's not detected by NEMU. Okay. Well, another technique which we just briefly talked about it, was anti-disassembly. You have the anti-disassembly techniques in the malware world, but thank you. but why not in the shellcode world? So we designed the 4 technique for anti-disassembly. So just trying to confuse the disassembler of the 2 test cases which we had, which was not very successful, as you can see. Like most of them got detected by NEMU, and libemu could detect half of them, which was, for us, was a failure, let's say. And anyway, there was 4 types. The simplest one, which everybody probably use, is using garbage bytes, right? And another one was like flow redirection, push-pop mask, and then code transposition. Well, another way to evade the emulation-based network intrusion detection system was using unsupported instructions. So we were thinking there might be some instructions which is not supported by the EBNIDS. So what if we use those unsupported instructions, for example, as a decryption key? So if the EBNIDS cannot emulate that instruction, as a result, it's because it can't run it, because it's not supported by EBNIDS, as a result, it will fail to detect the shellcode. So we used 4 types of instructions, not just the normal ones, but like the FPU instructions, 2 types of them, FNSTNV and FNSAVE, and MMX instructions, SSC instruction, and some absolute instructions, which are like not officially documented. And as you can see in the result, except 1 FPU instruction, FNSTNV, other instructions was not detected by any emulator, and as a result, they will fail to detect our shellcode. How? First, let's look at the unsupported instruction using MMX. So the basic idea is that what we'll do is that we want to put the address of ESP to EAX. So, but we copy this data before we decrypt the shellcode. So but we do it using MMX instructions. So if the MMX instruction is not supported by our EBNIDS, as a result, it will fail to decrypt the shellcode, and as a result, it can't detect the shellcode at the end. So we use like MMX instruction and use the MMX registers to copy the data. As you can see here, we first copy the address which is pointing, the ESP pointing to MM0, and then from MM0 to MM1 using MMX instructions, and then from MM1 to EAX. And if in the middle it couldn't get executed, then as a result, it will fail to decrypt the shellcode. So that was one example. Another one, which was a little bit different. I mean, you could use the same thing for another one, but you just have to be more creative. So this time, what we do is that we copy the address which ESP pointing to EAX, and then we copy the address of EAX using SSC instructions to XMM0 register using SSC instructions, and then we overwrite the address which ESP pointing. So basically, it means that you don't have that address anymore. We just overwrite it with some junk data, and so you don't have it, so you lost it. So if you want to get the address of ESP which pointing your register, you have to be able to copy from the ESP, from the XMM0 to like ESP or whatever. So I mean, your address is in that register, right? Which is a SSE instruction. And if you can't copy it, which means you are not supporting that instruction, then as a result, you will fail to detect the shellcode. And that was it. It's a question and answer time.
Yeah.
Shall we sit there? Or?